synchronous. It's not my favorite format. I would love to be in a room for all of you with all of you so that I could see all of your lovely faces and not be looking at black squares. But I think it's easier to give immediate feedback and help and answer questions in the classroom. Unfortunately, I think with COVID cases rising, they feel that it's safest to keep it under this format for the time being. I think they're hoping that by the summer and or next fall, we'll be able to go back to the regular format. But for now, this is unfortunately what we're stuck with. As I said, I'm going to, what I want to do is go back, and we kind of rushed over combustion analysis, and I do want to do that with you. So let me go to the slide on combustion analysis. And we're going to do a couple of problems with this. We're going to do the one that's here, but I want to do another one as well. This problem is a compound that is strictly made of carbon and hydrogen. So, and then we're going to do a problem that has something other than carbon and hydrogen. It's going to be carbon and hydrogen and oxygen. So let me switch my camera and ask if you can see that okay. So this is the problem that I just had up on the screen that's in the PowerPoint. A 1 gram sample of a compound produces 2.473 grams of carbon dioxide and 2.246 grams of water. Determine the empirical formula of the hydrocarbon. So we start with 2.743 grams of carbon dioxide, and everything has to be converted to moles. We need to work in moles. So 1 mole of CO2 is 44.01 grams of CO2. And that equals, when you do the math, that equals 0.0623 moles of CO2. Now I would point out that there's 1 carbon in carbon dioxide, so that we know there's 1 mole of carbon per mole of CO2. It seems trivial to do this because it's 1-to-1, but in the case of water, it's not 1-to-1. So I'm showing you that conversion here, 6 to 3 moles of carbon. Okay, so we have 2.246 grams of water, 1 mole of water is 18.016 grams. If you were on that to 18.02, that's fine. It probably wouldn't change your numbers too much. And this equals 0.124 moles of water. And as I said, there are 2 moles of hydrogen per mole of H2O. So that means we have 0.2492 moles of hydrogen. So essentially what we do is we have a formula that is 0.623 moles of carbon and 0.2492 moles of hydrogen, but our formulas have to be whole numbers. So we divide it, oh, I left out a 0 there, didn't I? That's 0.026. We have to divide by the smallest, so we divide by 0.026, and when we do, we get CH4. That is the empirical formula for this compound.
Professor,
Yes,
real quick, on the water molecule on that line, the 2 moles of hydrogen, is that because there's 2
yes,
atoms of hydrogen?
because there's 2 atoms of hydrogen.
Okay.
For every mole of water, it's 2 moles of hydrogen.
Then why wouldn't there be 2 moles for the carbon also, or for the oxygen in the other
In
problem?
the other, because we're not calculating oxygen from this. The important thing to remember is that we're taking our compound, which is, we don't know, if we assume we don't know the formula, so it's C, X moles of C and Y moles of H. Okay, so this is our generalized formula. And in combustion, we're adding oxygen to that to form carbon dioxide plus water. So we're adding the oxygen. The oxygen is not coming from our initial compound. The oxygen is coming from the air when we combust this. So what we're trying to do is determine the formula of the compound. So yes, if we were trying to calculate oxygen, yes, you would have to do it. You'd have to multiply it by 2, but we're not. The only thing that we can say is that this carbon in this compound ends up in the CO2. All of the carbon in the compound ends up in CO2. And all of the hydrogen in the compound ends up in water. In the next compound of combustion analysis I do, we're going to have a compound that is C, some moles of C, H, and oxygen. Okay. We can never consider the oxygen directly because we're adding oxygen. And so we can never do this directly. And I'm going to show you how you deal with that. It's actually much simpler than you might think. But the assumption that is made, and it is a valid assumption, is that all of the carbon in our compound ends up in carbon dioxide. All of the hydrogen in our compound ends up in water. Are there any other questions on that?
Professor,
Okay. Yes.
does dividing the lowest number always come out clean?
No, it does not. It always reduces one of your substances to 1. The lowest one goes to 1 that way. In this case, it was the carbon. What you have to do is you will end up with some sort of a decimal number. Sometimes you'll end up with a decimal number. Let me actually let you see my faces while I talk about this. You may end up with numbers that are, because of rounding errors, we could have ended up with 3.999 for hydrogen. That's still 4. You might end up with 4.998 or something like that. You can round those to the next integer. If you end up with something in between, you have to learn to recognize what are common fractions as decimals. If you end up with 1.5, that's really 3/2. If you want to clear that fraction, you have to go through and multiply everything by 2. If you end up with 1.33 as one of your elements, the mole ratio of one of your elements, that's 1/3. You have to multiply them all by 3 to clear the fraction. Or if you end up with 0.67, that's 2/3, and you would multiply by 3. Sometimes you might end up with 0.25 or 0.75. You would clear that fraction by multiplying by 4. If you end up, Chow had a question on a homework question today where they ended up with 1.8 and 2.8 and 1. 0.8 is a fifth, that's 4/5. So clearing that fraction, you have to multiply everything by 5. It's extremely unusual for you to get a problem that would be different than those recognizable fractions. So if it's 0.2 or 0.4 or 0.6 or 0.8, all of those would be cleared by multiplying by 5. So you have to learn to recognize common fractions as decimals in order to clear them. So the first step is to divide by the smallest number of moles. That gets one of them to 1, and then you look at what's left and you see if there's a common, if they're not all whole numbers, there's likely to be a common fraction that you can then multiply everything by to clear that fraction. So let me go back to my second problem. In this case, we have a compound that, sorry, I didn't mean to close that. In this case, we have a compound that contains carbon, hydrogen, and oxygen. Okay, so upon combustion, the entire mass of the sample is 0.8233 grams, and we produce 2.445 grams of carbon dioxide and 0.6003 grams of water. So I'm going to do the same exercise, 2.445 grams of CO2. And I have to convert that to moles. And when I do, I end up with, I'm actually going to do the 1 mole of C to 1 mole. And I do this exercise only because this first conversion leaves me in moles of carbon dioxide. I want to really be in moles of carbon. That's why I do that. So we have grams of carbon dioxide, and we end up with 0.05556 moles of CO2. The question often comes up, how many digits should I use here? Because you will often have rounding errors, and sometimes carrying more digits isn't helpful. Sometimes rounding to only 3 digits is more useful. I'm carrying 4 here because I started with 4 digits here.
Professor, wouldn't that be moles of carbon, not carbon dioxide?
Yes, I already made that change. So you're right, that should be carbon. So there we go. Okay, so I have 0.6003 grams of water times 1 mole of water is 18.016 grams. And I am going to multiply by, well, let me just say that this is equal to 0.03331 moles of water. And if I multiply by 2 moles of hydrogen, 1 mole of water, it's 0.06662 moles of hydrogen. Now, I need moles of carbon because this compound is going to be, if my generalized formula is CXHYOZ. I have all 3 of those. So I'm going to need to do, get moles of oxygen as well. And I do that by figuring out what mass of carbon, what mass of my original part of the mass of my original compound was carbon, and what part of the original mass was hydrogen. So I do that by saying that the mass of carbon is equal to 0.05556 moles of carbon times 1 mole of carbon is 12.01 grams. So that's going to convert moles into grams. and that is 0.6673 grams of carbon. And the mass of hydrogen is equal to 0.06662 moles of hydrogen. 1 mole of hydrogen is 1.008 grams. That equals 0.0617. Oh, excuse me, 7. I have that wrong. I've inverted those numbers on my calculator. 6715 grams of hydrogen. The mass of the oxygen then has to equal the total mass that I started with, which is 0.8233 grams of compound, minus the mass of the carbon and the mass of the hydrogen. The balance of this mass has to be oxygen, and that equals 0.0889 grams. Okay. Now I have moles of hydrogen, moles of carbon. I need to turn this into moles of oxygen. 1 mole of oxygen is 16 grams. And that comes out to be 0.00556 moles of oxygen. So I now have the moles of each of these components, and I have to do my formula. So I divide by the smallest, which is clearly the oxygen, 0.00556, and I end up with C10H12O, simply by dividing by the number of moles of oxygen. So this is my empirical formula. Okay. You can, one of the most common mistakes that students make in doing this kind of a problem when they have oxygen is in their compound is to try to calculate the mass in moles of oxygen somehow from the carbon dioxide in the water. And you cannot do that because you're adding oxygen from another source. You're adding oxygen from the air. And so you cannot calculate the mass of oxygen or the moles of oxygen directly from the amount of carbon dioxide and the amount of water. You have to do it by difference from the original mass. If your compound contains something else, maybe it contains another element, it might contain nitrogen, for example, you would be able to do the same thing. You'd be able to figure out the mass of the nitrogen in the compound by difference. It would be whatever's left over after you've calculated the mass of the carbon and the hydrogen. Or you might be given another experiment, or you might be given another value that says you also collected so many grams of an oxide of nitrogen. So that would help you if you were doing a more complex formula. But if the formula contains only those 3 elements, you can just do it by difference. Okay. Okay, so let me go back to this, and one last thing that I wanted to let me just make sure that I'm not going to freeze my computer again. I don't, for whatever reason, my computer is freezing when I change to that. When I change to that camera, my computer freezes and I don't know why. So let's see if we can do it this way. Okay, so we'll start over again, and we're going to go down to, oh, one thing I wanted to say about molarity, actually it's really more for dilutions. When you're using, whoops, sorry. When you're using this formula, when you're using this formula over here, C1V1 equals C2V2, or C, by the way, means concentration, which for our purposes is molarity. So you can use M1V1 equals M2V2. That's also okay. When you're using this formula, concentration, you know that molarity is moles per liter, but as long as your concentration values are the same, if you're given, your volume is in, if you're given volume in milliliters, you can calculate the second volume in milliliters. Or if you're given both volumes in milliliters, you can calculate concentration just fine, as long as they're the same. If one of these is given to you in milliliters and the other is given in liters, you're going to have to make a conversion so that you're dealing with the same units. So it doesn't really matter whether volume is in liters or if it's in milliliters, as long as it's consistent on both sides of the equation. That's the other thing that I wanted to tell you about that. And I did want to do, I was going to do a little bit about parts per million and parts per billion. This is the first question that I'll do this first question that's on this slide, and then we can answer any questions that you guys have, and then you can take your quiz. Your quiz will open up in time. So let me just go to this again. Here is the question. A 50-gram sample of industrial wastewater was determined to contain 0.48 milligrams of mercury. Express the mercury concentration in wastewater in parts per million and parts per billion. Well, 0.48 milligrams, if we have to get them in the same units. So 1 gram is 1,000 milligrams. So that equals 0.00048 grams of mercury. And that is contained in 50 grams of wastewater. When I do that math, it ends up 9.6 times 10 to the minus 6th. That is by definition, because it's 10 to the minus 6, that is by definition 9.6 parts per million. To get that into parts per billion, since the difference between parts per million and parts per billion is 1,000, it's simply multiplying this by 1,000. So that would be 9,600 parts per billion. Okay, these are the kinds of units that you deal with when you're dealing with toxins, when you're dealing with, in this case, it was wastewater, pollutants, all of those generally come out in parts per million or parts per billion. That's what the tolerances that are allowed for particulate matter in air or any kind of pollutant would be in parts per million or parts per billion. Yes, was there a question?
Yeah, could you actually go back? What was, I'm just confused on the concepts of parts per million and parts per billion.
Okay, so let me go back to the PowerPoint slide. But parts per million is the mass of the solute. In this case, in the case of the problem we did, it was the mass of the mercury per mass of solution, which is the mass of the wastewater. So we had 0.48 milligrams.
Wait, so
That's
it's massive solute. Sorry, I don't have the PowerPoint up here right now.
okay.
Parts per
It's
million.
the mass of the solute divided by the mass of the solution.
Okay.
Okay. And for parts per billion, it's the same thing, but parts per million is 10 to the 6th, or 10 parts per million would be 10 grams of solute per gram of solution, or 10 grams times 10 to the minus 6 per gram of solution. So you're only gonna run into that, as I said, for usually pollutants. Occasionally you'll find it in medicine as well, but much less often. Okay.
Can you explain again how you converted to parts per billion?
Yeah, the parts per million is 10 to the minus 6th. If I have 9.6 parts, or 9.6 times 10 to the minus 6th parts per million, I'm going to have 1,000 times that if it's parts per billion, because parts per billion is 10 to the minus 9th.
Okay.
Okay, I'm going to have
Okay.
1,000 times that if I'm counting them as parts per billion. So it's really just multiplying the answer by 1,000,
Okay. Thank you.
because parts per billion is 10 to the minus 9th. So that's really it for chapter 6. I think there's another problem there that you can work on as a practice problem to see if you can work through them. The question let me tell you about the quiz today, because I'll open it up in a second and you guys can start it. It's a 20-minute quiz. There are 3 questions. The first one is a numerical answer. You do not have to upload any work for that. The second 2 questions, there are 2 questions that require work. I'll even tell you what they are. One of them is calculating an empirical formula. The second one is a M1V1 equals M2V2 problem. So except for that came from a little bit later in the chapter. The first one comes from early in the chapter. We will have another quiz on chapter 6 to do a couple more practice type questions on this, but we'll do that sometime next week. Probably Thursday. The fourth question is just your upload question. So you have 2 questions you have to show me work on, and the fourth question is uploading that. It says chapter 6 quiz 1. You can
It's
open
me,
it anytime.
Professor.
Yes.
For the video quiz, when is that due?
The nomenclature, the video quiz, I extended the due date on that until I think Monday or Tuesday. I think Monday. You can do that as many times as you want, and you have until Monday to submit your video.
All right, perfect. Thank you.
Okay. So you guys can start your quiz anytime you're ready.
Professor,
Yes.
is there a situation where the parts per million we will have like 10 to the 6th, or we always have 10 to the 6th, right?
If you're giving the units parts per million allows you to write the concentration without having to write 10 to the minus 6.
Okay.
Okay. The concentration I just calculated was 9.6 times 10 to the minus 6th per gram of solution. 9.6 times 10 to the minus 6 grams of mercury per gram of solution. in order to write that without having to write times 10 to the minus 6, I say that it's 9.6 parts per million.
Oh, okay.
It's just a way of getting rid of the scientific notation.
Okay.
Okay?
Sorry, professors. One more question about the chemical nomenclature
Yes.
quiz. For how are we taking a video with our phone and then uploading it?
Yeah, you can take a video with your phone. That's fine.
Okay, thank you.